So, Chapter 1, Functions and Graphs, and here are all the wonderful things that we're getting out of 1.1. And 1.2 is even packed with more, so each one of these sections, it always seems like by the end of the year in pre-calculus, students are like, we only got to, chapter 6, chapter 7, chapter 8. Yeah, because every chapter has a ton of stuff in it. So we will be able to set up models to represent real-world phenomena numerically, algebraically, and graphically, combine algebraic, graphical, and numerical methods to solve and verify solutions. In the case of word problems, that's how it all works. We have to put it all together. Use the problem-solving process to model and solve those real-world applications, and understand some of the limitations of the graphical method, and that we're really going to see today. And we'd like to think that our graphing calculator can do absolutely everything for us, but there are certain features that when you use them, you don't get to see everything that the graph is trying to show you, so we have to take a look at that too. And we are way back here talking about heavy rainstorms. Mexico is evacuating some cities because of another hurricane, and it's just one of the things that places like that, and in Texas and anything that borders the Gulf of Mexico, they have to think about this, and they have to plan for this. So it brings a whole new meaning to the position of city engineer as they try to figure out, do we have to evacuate? How much time should we give people to get out of this region? And one of the other stories this morning, Cancun, which hardly ever gets hit with the hurricanes, is being hit with a hurricane right now. And there's some Americans that went down there, without checking the weather forecast first. So now they're spending their vacation in a school gymnasium packed with people who could not get out in time for this hurricane. So it's just something it's a realization for those people, not for us here, but they just have to plan for these things. So, because of an anticipated heavy rainstorm, the water level in a reservoir must be lowered by 1 foot. Opening spillway A lowers the level by this amount in 4 hours, whereas opening the smaller spillway B does the job in 6 hours. There's an emergency. They want to open them both. How long will it take to lower the water level by 1 foot if both of those spillways are opened? Somebody realized, oh my gosh, we never tried to lower the water level and all this rain is going to come. So with this problem, what we want to do is we want to think of these as a rate. Now, part of the reason we want to do that is because we've already gone through the rest of the section and we see that this is kind of built on fractions and solving equations that have fractions in them. And a normal rate for us would be like distance divided by rate equals time. Those type of rates we've worked with before. But in this one, I see that what they really want to do is lower it feet per hour. That's what they're trying to figure out. How is that going to work? And right now, we know that they're going to go ahead and use spillway A and spillway B. And they want to use those two together, so they want to add those two, and they want to see just how long is it going to take for all of that to work together. So, what I don't know is how long it's going to take for both of these to make this happen. So X is going to be time to lower with both spillways open. The goal is the same for each one of these spillways. They want that water to drop 1 foot. So for A, it's 1 foot in 4 hours. For B, it's slower, must have smaller pipes. 1 foot in 6 hours. But together, how long will it take for that same 1 foot to fall? So again, knowing that this whole chapter, or this section actually, has been about writing things as fractions and solving them, we have this. Well, there's our model. 1 foot, 4 hours. 1 foot, 6 hours. 1 foot, how much when they're working together? And we realize, well, this is a piece of cake. I mean, all we have to do is find the LCD, multiply by the LCD, solve this algebraically, and we'll have it. So the setup is actually the part that takes some thinking. So what's the LCD for 4, 6, and X? 12 and the X. We're going to multiply all three terms by 12x. We're, of course, going to do some canceling. We'll reduce in here with the 4 and the 12 will get us 3x. The 6 and the 12 will get us a 2x. And over here, the x's will cancel, and we'll get 12. And yeah, it seems a little too easy, but that's okay. I mean, we're going to get the right answer in the end. So it'll be 5x equals 12. Divide both sides by 5. And now this is a real world problem, so they want to know how long is this going to take. And 5 will go into 12 twice with the remainder of 2. And you won't normally see me write things as mixed numbers because we don't do that at this level of math. But we do want to change this into a decimal anyway. So if I have 2 and 2/5, I realize that's going to be 2 and 4/10 hours. But like I said, this is the city engineer, and he wants to tell the boss exactly how long this is going to take. He's not going to say 2.4 hours. He's going to say 2 hours and blank minutes. So what we would do is take that 0.4 times 60. Did you already do it in your head? How many minutes are we talking about with 0.4 times 60? Okay, I'll do it up here. Too early in the morning to ask you to do that, huh? All right, 24 minutes. So now we can tell the mayor and all the emergency personnel, in 2 hours and 24 minutes, we can get that water level down, and hopefully that'll help. And that's where we see this interpret piece here, which is, hey, you're the person that has to deliver this message. You want to answer this as clearly as you possibly can. So you would tell them with both spillways open. You want to be as clear and just make it so that nobody can miss what it is you're talking about. With both spillways open, it will take 2 hours and 24 minutes to lower the water level cross my T, lower the water level by 1 foot. Because you know what's going to happen next, right? Somebody from the emergency personnel is going to say, okay, but I heard worst case scenario, we might get 18 inches of rain. And then it's, okay, well, let's go again. Let's figure out what's going to happen here if it's 18 inches of rain. So this is kind of the initial, this is going to help, but what do we know is going to come in the future? All those predictions change so last minute anyway, especially as hurricanes approach the coast. So now, that graphing calculator. At some point, you start thinking this little bugger can maybe even do the laundry for you. I mean, it does so much stuff, but it does have its limitations. There's only so much it can do. So why don't you grab your graphing calculators? I'm going to use mine up here since I'm recording this lesson. Anybody need one? Should I go grab one for somebody? Everybody's good this morning? Okay. So, word of caution about the graphing calculator. There are certain functions in it that produce what's called a graph or failure. So Grapher failure is when the calculator produces a graphical model that misrepresents the graph, basically, you know, the situation you're studying. So this one says, seeing a grapher failure. We're going to look at the graph of y equals 3 minus 1 over the square root of x squared minus 1 with a window, quite frankly, I have never used in my life except for this example right here, zoom decimal. And it's because zoom decimal is based on graphing starting with 1.1. It has a focus on tenths as its decimal. But this is what they want us to see. So we have to be very careful. We're going to need parentheses to get this thing to understand, our calculator to understand that this is a big fraction. Pardon me, big fraction. So we're going to have to make sure we use at least one set here to make everything show up. Because the question is, are there any x-intercepts? So let's go see. We're into that y equals, and I better get my glasses, 3 minus parentheses, and then we have the 1 on the top divided by, and then we have the square root of x squared minus 1. Then I want to make sure that I get everything in here correctly, so I have to pop that out of my square root symbol and then finish off that parenthesis so the calculator knows, hey, big fraction here, 1 over the square root of x squared minus 1. Now, like I said, they want us to do zoom decimal, so zoom, and that would be number 4, which we would never use, you know. We're much more appropriate to grab zoom 6, which is our zoom standard window, but they're letting us know this will produce a problem. And we look at it, and it looks like the range doesn't start until we get up here close to positive 1 somehow. And that's why we just use the graphing calculator to verify. But now let's hit zoom 6 like we normally would anyway. The zoom decimal is not something you use at this level. Well, now we can see, yeah, it should hit. But if you accidentally hit the wrong button, you may just say, oh, the calculator's always right. So again, what we're doing is we're doing the algebra. And then, yeah, we'll verify with the graphing calculator, but we're not going to turn it all over. Ben. Oop. It said, no, I'm not doing it. And that was when you hit zoom decimal?
That was zoom 6 or this graph.
Oh, you got your stat plots on yet. That's why it's yelling at you. Let's turn those off. Now it shouldn't yell at you anymore. Yeah. Anybody else have anything goofy showing up? Okay. So, quick reminder, because Ben won't be the first and only one that this happens to. If you have stat plots on, sometimes your calculator refuses to do the normal graphing like we're doing here. So if it gives you a error in dimension, take a look and look for those little black boxes that say your stat plots are on at the top, and that's usually the problem. All right, so it says, are there any x-intercepts? And what we would want to do is figure out, well, where are the zeros, you know? So we'd put a 0 in for y. And we would solve this algebraically and then just back it up with what we could see on the graphing calculator. So we'd subtract 3 from both sides. Divide both sides by -1 to get rid of those negatives. And then we'd go ahead and think of this as if it were a proportion. You could slap a little 1 down here if you want to, but we'd cross multiply. That would be the easiest way to solve this. So we would have 3 square roots of x squared minus 1 equal to 1. And we just keep going. We divide both sides by 3. Got to get rid of the square root. How do you get rid of that? You square it. Square both sides. And actually, this is the step where you would want to start thinking, okay, when you raise both sides of an equation to an even power, it's possible that you will get extraneous solutions. That's one of the things that happens. So at this point, you might think, hey, I better check this with my graphing calculator when I get done. So now we would add 1 to both sides, which is 9/9. And we would take the square root. X equals plus or minus the square root of 10 over 3. So now, like I said, because we had to raise both sides to an even power, it's possible that we get extraneous solutions. So that's where we'd grab the graphing calculator and make sure, hey, is this really going to hit at the square root of 10/3? And if we use Zoom Decimal, we'd go, wait a second, what happened here? But if we use Zoom Standard, we're going to see that it hits the x-axis in those two spots. And, you could find them as a decimal and verify that they're going to be the same thing as the square root of 10/3 as you go through that. So, graphing calculator is not a cure-all. You don't want to use it for everything, but we definitely want to use that when we are talking about, things with restricted domains like this one, because we have the square root of x squared minus 1 down here. And we talk much more about domain in section 1 too. So there's two issues. We can't divide by 0, so it can't be 0. And we already know that the only way that we can do this normally would be if x squared minus 1 is greater than 0. Now, why do I say that? Because it has an x squared in it. Of course, everything is going to be positive. No matter what we put in there for x squared will be positive. So we could continue on and solve it. But that would bring up a little absolute value piece there, because again, we have to guarantee that it's going to be positive. Now, don't worry too much about that. That's more in the notes of 1.2. Restricted domains tell us, hey, something's up. The calculator might not like this. Whenever we have to raise to an even power, it's possible that the calculator may not like it. But it's always a good way to check. It just is a good way to check. So, down here, the other thing the calculator is famous for, hidden behavior. It only has so many pixels. We're not looking at a computer screen when we look at our TI-84 Plus. If we were, we wouldn't see those little steps sometimes that show up when we're graphing. It would be nice, smooth curves all the time. And those of you that have the newer color ones are usually nice, smooth curves. Every once in a while, you get a chunky-looking graph. But there can be hidden behaviors, and it's when the window is too large, so we can't see all the details that are there. So we're supposed to solve graphically this little monster here with all these wonderful decimals in it. Let's get it into our graphing calculator, and then we'll take a peek. First of all, we know that one's not going to be factorable. It's a mess with all those decimals in there. So we would have to try the graphing calculator. Oops. There we go. Always bothers me that I have to punch it in so slow up here. If I get ahead on the keys, then it doesn't take what I've punched in. Well, there's that monster. And let's say we do zoom 6, which, we normally would. And we see, looks like it definitely crosses at one spot here. But I'm missing a whole lot of the up and down part of this graph, and on a test that wouldn't be okay. I'd want to see everything that's happening here. So I'd mess around with my window a little bit and say, looks like it's almost going straight up or down. Maybe I better try like -100 to 100. graph. Whoops, one of them didn't take. Nope, that's what I was talking about. I got ahead of it. I have to punch slower. Come on. Why won't it take it? Because my recorder's in the way. There we go. Better. Still not able to see the whole thing. Try window again. Since it took so long for me to get my zeros in there, did anybody try big enough that you're seeing the whole thing yet? What'd you get? What was your window? Ooh, took a while, huh? Oops. Yeah. And if we look at the equation for the graph, a lot of that's going to come from the fact that the last number was 229.5, you know? So now we can see the whole thing. Well, now it would be easier for Blinky to find this intercept for us. It could have done it before, but it's a little bit easier for Blinky when we can see the top and bottom pieces. So second trace above and below the x-axis. Number 2. And Blinky's got to find his way over here. Come on, Blinkster. A little farther. There we go. So below it is to the left. Above it is to the right. And there it is. Negative 90. So there's one of them. How many zeros is this supposed to have? 3. This is a cubic. It's supposed to have 3 zeros. So looking at what we see on the graph, we might be tempted to say, I bet you this just has one more zero, but it's a repeater. Because remember, you get those repeat zeros when it's hitting tangent to the axis. But from this look, I can't tell. So I would hit zoom 6 again, because now my focus is not so much on that zero that's way out on the left here. My focus is on this region around 1, 2, 3, 4, 5. Something's happening over there. And this is where that zoom box really helps out. So zoom, number 1. We want to get Blinky in the position that would be an upper right-hand corner of a box. And press enter. And then we use our down and right keys to form the box. And then press enter. Well, by golly, look at that. There are 2 more real zeros there. We can see them now. Without the zoom box, it looked like it might be a repeater. It might be a tangent over there. So now it's second trace, number 2. And this time, the leftmost intercept is going to be above. And then the right side of it will be below. 5, 0. That's a nice one. And then we have one more, which probably isn't a nice one, but we'll see. Below it is left, and above it is right. That's not too bad. 5.1. We can live with that. So 5, 0, and 5.10. The graphing calculator is famous for this hidden behavior piece. You know, you just can't assume things are happening. When something goofy happens where our eyes are supposed to be, like in this situation for the x-intercepts, we have to say, oh, they might be trying to hide something from us here. Let's zoom box on that. And then in these boxes, it just has the sketch of what we were talking about. And actually, negative 500 to 500 would have made it a nice little curve for us as well. But negative 1,000 to 1,000 covered all our bases. And then you had to get a close-up, a zoom box on what was going on. So we can't just trust the calculator. We have to think about what's going on. This is a cubic. It should have 3 zeros. Either that's a repeater over there because it's tangent, or there's a couple of them there that I can't see because the calculator is not clear enough. I need to zoom in. So basically when I ask you how many zeros we're talking about the fundamental theorem of algebra, and that was the 3 zeros. We know how many there are. We need to scout it out, and we need to look for them, which would have been so much easier if this were factorable, but we don't know how to factor all that good stuff in there that has all those decimals. So you have to change your window and go from there. And I am pretty sure this is it. So the main question here down at the bottom, I don't know if that one even shows up in your packet, is which viewing window is best? And the answer to that is we had more than one viewing window that was best. It depended on what we needed. So there may be more than one. Best window. It all depends on what you have to see. And if you can't see it clearly, then the cursor is not going to be able to work for you and find you what you want. So make sure it's clear. Mess with your window if you have to, and you'll have what you need. Questions about what we covered today? Basically, it was just 2 topics, 2 objectives. You know, we talked about a rate problem, rate word problem, and then we talked about the graphing calculator features. You're good? You're looking tired, but you're good? Okay. So that was Monday, Tuesday, Wednesday. Right there. And yeah, do remember gray oval problems are problems that are meant to be done without a calculator. And again, that's our best practice anyway. You know, do it algebraically and then use that graphing calculator. Now, I think it's a blue. The extra word problems, I think it was blue. Yep. So it's going to be the blue worksheet. I was going to ask if you wanted to, should we start 1, 2? But you're not looking like the peppiest group this morning here. So would you rather just work? Okay, we'll just work.